For this example now, we'd like to draw the electric field lines and the equipotential lines around our system of charges, where each of these charges is 1 nanocoulomb. We'd like to find the electric field and electric potential at the point P shown here. These are separated by 2. P is 2 meters out. So for our electric field lines, we're going to follow the rules. We know we go out of a positive and into a negative. The lines can't cross, and the number of lines is proportional to the size of the charge. These are both positive, so what'll happen is I'll come out of this positive charge and go straight up. And then for this one, they're going to be symmetric. Go straight up. This one will go straight down. This one will go straight down. And then if this one comes out, it can't go over to the positive. It'll be pushed up something like this. Okay, they're equal charges, so they should have equal number of lines. This one will go out. This one will go out. Go out. Go down. Go down. Go out. Come down like this. Come down like this. Okay, so this is more or less what the electric field lines will look like. We can label those with an E. Our equipotential lines also have to follow the rules. Equipotential lines can't cross, and they have to be perpendicular to the electric fields. These are a little tricky to draw, so we'll do our best. So everywhere I'm making these electric fields cross the electric potential, the equipotential lines are crossing the electric field lines. I'm doing my best to make sure they're perpendicular. Being close to the charge, the equipotential lines will be a little closer together because the potential is a little stronger. And then they'll spread out as we go out. Pretty tough to do a good job of keeping them perpendicular, but they'll look something like this. Here's where a FET simulation can come in handy, which is also part of this problem to check your answers with a FET simulation. So we'll give that a try after we've done the work here. When you're drawing these on a test, not a bad idea just to show that you know they have to be perpendicular. Drawing certainly can get away from any of us. So something like this is what our equipotentials are going to look like. We'll label those EPL for equipotential lines. So we've got our drawing done. Find the electric field and the electric potential at the point P shown. I'm just going to grab a fresh sheet of paper here. So I've got my charge 1 right here. There's my positive. My charge 2 right here. There's my positive. My point P is right here. 2 meters. 2 meters. Q1 equals Q, Q2 equals Q. My net electric field at point P will be the sum of the 2 electric field vectors. The electric field due to charge 1 will look something like this. It has to point away from charge 1. My electric field due to charge 2 will have to point away from charge 2, E1 and E2. Let's put in my coordinate system X and Y. Electric fields are vectors, of course. So to calculate my net electric field, the sum of my electric field is E1 plus E2. My electric field E1 is K times Q1 over R1 squared, points to the right, so that's positive I hat. I've written R1 here, so I should show R1 in my diagram. R1 is from charge 1 to point P. That's going to be 4 meters. And then E2 is K times Q2 over R2 squared, also to the right. R2 is from Q2 to our point. R2 is 2 meters. Let's see. Q is the same for both. Q1 equals Q2 equals Q equals 1 nanocoulomb. So if I just want to do some grouping, K times Q, 1 over R1 squared plus 1 over R2 squared, that's I hat. K is 8.99 times 10 to the 9. Q is 1 nanocoulomb. R1 is 4 meters. R2 is 2 meters. I get a net electric field of 2.81 newtons per coulomb. So there's my total electric field at point P. For my total electric potential, I'll do a similar sort of thing. B is V1 plus V2. Remember, potential is a scalar. We don't draw any arrows and we don't put the arrow on top. K times Q1 over R1 plus K times Q2 over R2. We can do our math here as well. So K is 8.99 times 10 to the 9. Q1 and Q2 are both 1 nanocoulomb. 1 times 10 to the minus 9 coulombs. R1 is 4 meters. R2 is 2 meters. We get a net electric potential of 6.74 volts. So there's my net field and my net potential. Then the problem also says check your answers with a PhET simulation. Okay, I'm going to point the laptop at the screen again. And let's see if we can do that simulation without me moving the iPad too much on you. So we go to PhET electric fields. We'll put in a positive charge. Each of these grids is a half a meter. So 1, 2, that's 1 meter. 1, 2, that's 2 meters. And our point P is going to be right here. We'd like to draw our equipotential lines. So let's try and draw those lines. So I think I'm going to try and draw one at 9 volts. We'll hit draw. I'll draw one at 18 volts. I'm not going to try and be super perfect here. In all fairness, I'm not a terribly patient person. There's 18 volts. Then let's go 27. So I'll space them all by about 9 volts. 27 over on this side. And just to go in one more, let's also try 36. 36 over on this one. Okay, so there's our electric field lines. That's the white arrows. Equipotential lines are the green lines. We'd like to measure our electric field at our point P. So that was 2 meters away. So there's 1 meter. There's 2 meters. The electric field right here says 2.77 volts per meter. We got 2.81. That's pretty good. That's pretty close. To measure our electric potential right here, we'll put our sensor right on top. 6.705. We had gotten 6.74. So our PhET simulation confirms what we found in our